Alright, so now we're going into 5.2. In 5.1 we talked about the natural base e. And we talked about its function, right? So the function of the natural base was y was equal to e to the x. Okay. Now, again, these type of functions have inverses. So um, we know inverses to be like plus and minus. Those are inverse operations. Multiplication and division are inverse operations. And then last unit we learned about radicals, right? So the nth root of a, and the inverse of the nth root of a was a to the n power. Now, this might get a little confusing because we are still talking about exponents, but not in the same way. So here we had often a variable being raised to the power of 2, and the inverse operation of that would be to take the square root of x, right? Well, the difference here is that for exponential functions, the variable isn't in the base. The variable for exponential functions is the exponent, okay? And now there's a difference then, because this will not undo, radicals will not undo this operation here, because the x is in the exponent location and not as the base. And so today we're going to learn about logarithms, which are the appropriate inverse to exponentials. Logarithms are the inverse to exponentials. So, let's go over some ideas first. So, in this first exercise, in exercise 1, it says to work with a partner, and you can work with someone that you know, or you can just do this in your head, but it wants you to find the value of x in the exponential equation. So again, exponential equation, where x is the exponent. X, or the variable, is in the exponent. Okay? And explain your reasoning. So let's go ahead and look at this. So for a, it says 2 to the x power is equal to 8. So most of the time in the last unit it would be like x cubed is equal to 8. So you'd have to take the cube root of both sides and you would learn that x is equal to 2, right? 2 to the third power will give you 8. Well, here it's opposite, where we have 2 to what power is equal to 8. And I know that if you raise 2 to the third power, you'll get 8. So here, for a, x is equal to 3. For b, 3 to what power gives you 9? Well, I know that you'd have to square it, so x would have to be equal to 2. For c, so you have 4x to the second power. So 4 to the x, 4 raised to what power is equal to 2. And for that should give you 1/2, right? It would have to be 1/2, because 4 to the 1/2 power is equivalent to the square root of 4, which is equal to 2. Okay? For d, I have 5 to what power gives you 1. Remember that anything to the 0 power gives you 1. So that means x would have to be 0. For e, 5 to what power would be 1/5? Well, this is the reciprocal of 5, so that means it would have to be a negative exponent. So x would have to be equal to -1. For f, 8 to the x power is equal to 4. So let's see, if you had 8 to what power would be equal to 4? Now these ones get a little bit more trickier, right? Not everything will actually give you an easy solution. And so that's where logarithms actually come in handy. We could perform logarithms on these type of more tricky situations in order to find the value of x. So that actually gives us a perfect segue into what is the definition of a logarithm. So here is a logarithm. Log base b of y is equal to x. So let b and y be positive real numbers. So they have to be positive, they can't be negative, and they have to be real, not imaginary. And b cannot be 1, equal to 1. So b has to be greater than 1. The logarithm of y base b is denoted by this and defined as this right here. Okay? Now, log base b of x is equal to x if and only if b to the x is equal to y. So right here, this is how you can convert. This is like converting. You can go either way. You have b to the x power is equal to y. You can convert that into a logarithm. So, for example, up here, for 8 to the x power is equal to 4. So in this case, b would be equal to 8. X is still x, but y would be equal to 4. I'm going to convert that into a logarithm. So this is going to be equal to, again, I'm going to convert it to log base b, which would be 8, of y, which would be 4, and this is equal to x. And from there we can use calculators to help us find out what this is. But anyways, that's just an idea of how we can use logarithms as like inverses to help us find the value of x when it's an exponent and not as the base. So in this first example, we're going to rewrite equations into exponential form. So right here, this is exponential form. Right here, this is logarithmic form. Okay, so here we're in logarithmic form, and we want to convert it to exponential form. These are equations. So here, again, I would just recommend looking back to here. So again, if I'm going to convert this into this, I need to make sure that I'm matching up x to the x, y to the y, and b to the b. Now, an easy way that it's easy for me, but whenever I learned this, I kind of just thought here, the base is the base over here, right? So the base over here, which is b, is also the base number over here. So I always start with that. So 2. Now, this right here is your exponent. Okay? So this is your base. This is your exponent. Okay? So this means 2 to the 4th would be equal to, and this right here is what it's equal to, 16. So for me, in my head, what helps me is I kind of draw like a circle in my head. So I go from here to here, from there to there. So here to here to there to there. And that's how I kind of remember my conversion from logs to exponential. And this is true. We know 2 to the 4th power is equal to 16. So go ahead and try these on your own. Maybe take a second to pause, try it on your own, and press the play video again. So I'm going to continue on, but so here, this is the base, so it's going to be 4 to the 0 power is equal to 1. And remember that anything to the 0 power is equal to 1. Okay, for here, that's my base. 12 to the 1 power is equal to 12. 1 over 4 raised to the negative 1 is equal to 4. And all these hold to be true. So thus we've just shown that these two forms are equivalent to each other. These two forms are equivalent to each other, just written in a different way. One's in logarithmic form and one's in exponential form. Okay, now here we're doing the same thing but in reverse. So we're going to go from exponential form to logarithmic form. Okay, so if you need to, make sure you have these handy right here. But I'm going to use my same thing. I know that this is the base. I know that in the logarithm, if I'm converting from exponential to my logs, that number right here is the base. So log base 5. Okay. Now this number right here will be what's called it's going to be the y value, in here. Okay, so that's going to be 25. So log base 5 of 25 is equal to the exponent. So remember that it's equal to the exponent. So the exponent always goes on the other side of the equation. So here's the base. Here is what you're taking the log of. So log base 5 of 25, and this is the exponent. So likewise, I'd recommend maybe taking a pause, see if you can write these quickly on your own, and then press play and see if you get the same thing that I do. So from here, I know that this is going to be log base 10 of 0.1, 0.1 I guess, is equal to -1. For C, log base 8 of 4 is equal to 2/3. Then log base 6 of 1 over 2/16 is equal to -3. Okay, so hopefully you guys were able to get something like that, and hopefully you guys find a method that works for you. So what might be easy for me might not be easy for you. So maybe try and think of a way or establish a way that makes it more easy for you to rewrite these equations in both ways. Write it down in this column right here, your process. Write down what you think will help you. Okay, now in these ones we're actually going to be evaluating these expressions. Okay, so log base 4 of 64. So if we're trying to evaluate it, we know that this is equal to something, right? Log base 4 of 64 has a value. So in other words, for me, it just makes it easier if I just set this equal to x, as x is the variable, and I'm trying to find what this is equal to. So that helps me. And now, since I know how to convert this to an exponential form, maybe that will help me. So I'm going to convert this to exponential form. And if I'm going to convert to exponential form, it's important that it's an equation. So on its own, right here, that's not an equation. This right here is an equation. So exponential form would say that this is 4 to the x power is equal to 64. And so we have to ask ourselves, what power does 4 has to be raised to get 64? And I know that that would have to be 3. 4 multiplied by itself 3 times is 64. Now for B, remember that this is, if I'm evaluating it, it's going to give me some value x. So now that I have an equation, 5 to the x power is equal to 0.2. Now, 0.2 is just 1/5, right? And we actually already solved something like this earlier, but x to 5 to the -1 power would give me its reciprocal. So I know that x would have to be x would have to be -1. Sorry, and over here, this isn't the answer. remember that we were supposed to evaluate log base 4 of 64, and we found that x was equal to 3, so that means log base 4 of 64 is equal to 3. That's evaluating the solution for the logarithm. Likewise here, we know that x would have to be raised to the first power in exponential form, so log base 5 of 0.2 would have to equal -1. Okay, now here I have log of, so I'm going to rewrite this to be 1 over 5, okay, raised to the x power is equal to 125. So here I'm going to have to need an, x is going to have to be negative, because this right here is not in a fraction, and this one has a 5 in the denominator, but I do know 5 to the third power is 135, so that means x would have to be -3 if I wanted to get that. So x would have to be -3 in order to get 125 in the numerator, so that means log of 1/5, log base 1/5 of 125 is equal to -3. And here, so again, I'm looking for the value of this expression. So 36 to the x power would be equal to 6. And in order to get that, I would have to take the square root. So x would have to be raised to the half power, which is the square root of 36, which is equal to 6. And so that means log of 36 is equal to 1/2. Okay. So hopefully those aren't too bad. Now let's talk about a common logarithm and a natural logarithm. Now remember last time how I talked about exponential functions in general, which was y was equal to b to the x, where b was a number greater, didn't equal 1, so b was equal to 2, 3, and this is how you got exponentials. In general, this was called exponentials, right? And then we also talked about specifically there was a specific exponential function which was y was equal to e to the x. Now this is an exponential function, an exponential, however it's a special type of exponential, and this was a natural base. A natural base function. Still an exponential function, but natural base. Natural base being e. Okay. Likewise, logarithms have a similar idea. So a common logarithm is a logarithm with base 10. And it's just basically, it's like pretty much like a generic logarithm. Kind of like over here. This is like a generic exponential. The natural logarithm, though, is a logarithm, is a log with base e. So e would be the base, and we call that the natural logarithm. Okay. So now this is what it would look like. A common logarithm would look like this: log base 10 of x, which we just write as log of x. So basically, if you see log of x and it doesn't have a subscript here, then it's assumed that the base is 10. Okay? Now, log base e of x, we actually just write it as this: ln of x. ln of x. I don't know why it's ln, because we call it natural log, but ln of x. And again, if you see ln of x, then right here, it's assumed the base is e. So we're going to use calculators to help us, and I'll show you how you can use logarithms and natural logarithms in your TI-84s. So for here, it says evaluate a, log of 8, and b, natural log of 0.3, using a calculator and round to 3 decimal places. So let's go in here. Alright, now the log button is on the left hand side. The log and natural log button is on the left hand side of your calculator. It should be right next to the left of the 7 and the 4 buttons. So you can see them there. Now we were looking to find log of 8. Okay, and notice that it gives you the parentheses, so that's where you're going to put in. Now remember that because notice that it doesn't show the base here, and that's because it's automatically programmed to show to have a base of 10. So this is like saying log base 10 of 8. And when we click enter, we get 9.03. So this is equal to 0.903. And similarly, again, we can use a natural log. Okay, there's a natural log button, and we want to find the natural log of 0.3. Enter. That gives us -1.20, and then round up, so that would be 4. Alright, that's all you got to do when evaluating using a calculator. You got very easy, convenient programmed buttons that will do the math for you. Okay, now to come to our conclusion with these last 2 examples, we're going to talk about using inverses. Okay, now by the definition of a logarithm, it follows that logarithmic functions, so again, log base b of x is the inverse of the exponential function f of x is equal b to the x. Okay, so that means that we can use these in our equations, or like to take inverses, right? So it's the same thing as like taking x plus 1 is equal to 2. Well, to undo this, I have to subtract 1 from both sides, so x would be equal to 1, right? So similarly, we can use these inverses to help us. So make sure you understand what's going on here and what's being said. So g of f of x and f of g of x, right? So those are compositions. So again, if g of x and f of x are equal to log base b of x and b to the x respectively, well, if you compose the compositions together of them, you're going to get x, which is what we talked about last time as the definition of an inverse function. Okay? So notice here, let's say that you had, so you notice here that log base b of b to the x, that if right here the base and what you're taking the log of, if they are the same, it's like they cancel out and you'll just be left with this exponent here. That's why x is equal to x. Okay? Likewise, if you have b and you have an exponent of log base b of x, well, this base right here and this exponent of log base b cancel out, and thus x would be equal to x. So let's try and put this into practice. So for a, it says simplify 10 raised to the log of 4. Okay. Now, what we talked about earlier is that if there is no subscript, assume it's a base of 10. So really, this is like saying 10 being raised to the log base 10 of 4. Okay, if that's the case, these cancel, and you're just left with 4. And that we just simplified this expression right here using inverse properties. For b, you have log base 5 of 25 raised to the x power. Okay. Now, here's the thing. These numbers are not the same, right? So if we're going to use inverse properties, these have to be the same. So remember how this b and this b was the same, they were the same values, so we could cancel them out. So I'm going to rewrite this expression that we have here to be log base 5 of 5 squared, and that's being raised to the x power. Now, this is a power to a power, which means that I can multiply the exponent, so this is log base 5 of 5 raised to the 2x power. Now, look, we can use inverse properties right here. These are the same. b, the base is the same as what you're taking the log of, which means they cancel because they're inverses of each other, and I'm just left with 2x. And there you go. That's really as hard as it can really be right there. Really not too bad. And now finding inverse functions. So we've already done this in the last one, so you should be familiar with how to find these inverse functions. Remember, the steps of finding the inverse functions is we're going to write this as y is equal to 6 to the x power, right? And then we're going to write this as x is equal to 6 to the y. Okay? Now, what I'm going to do, thing is, I need to get y by itself, right? So I'm going to perform the inverse operation of this right here, which would be a logarithm. So on the right side, if I take the log base 6 of 6 to the y, that means on the left side, I have to do the log base 6 right there. And this is going to be to the x. So the log base 6 is basically what I'm doing to both sides. I'm taking the log base 6 of both sides. Which is good because here I have a matching base, and I'm taking log base 6 of 6, which are inverses of each other, so they cancel. So on the right side, here I have log base 6 of x. This is just going to be equal to y. And there you go. We just found we got y by itself, so the inverse function is g of x is equal to log base 6 of x. Alright, now let's go to b. So following the same process, here we already have y is equal to a function of x. So let's swap their location. So x is equal to the natural log of y plus 3. Remember that natural logs have a base e, not 10. Okay? Now, what we can do is we can rewrite this as an exponent, right? So here it's log base e. So I'm going to write this so that it looks a little bit more familiar. So log base e of y plus 3 is equal to x. Now what I'm going to do is I'm just going to rewrite this in exponential form. So remember that the base is e of if I'm going to write this in exponential form. So e to the x power is equal to y plus 3. Okay? Now by doing that, I can see here that I just have y plus 3. So to get y by itself, I'll just subtract 3. So y would be equal to e to the x minus 3. And there we have y all by itself, so here is the inverse. Alright. Okay, that should pretty much do it for this lesson. So I think logarithms, they might seem a little bit weird at first, but their properties and their ideas are actually a lot easier in practice. And logarithms are actually where I found myself starting to enjoy math, because making use of the properties and making use of the inverse was actually quite easy. So I hope you guys have a similar experience going through these logarithms and the practice problems here. So anyways, if you have any questions, make sure you email me and let me know.